So far in this class, we've dealt with problems, thermodynamic problems, with systems that we assumed or at least treated as chemically homogeneous. We've not talked in detail about the chemistry of some of these systems. We've not really dealt with problems involving some mixture of nitrogen, oxygen, helium, hydrogen, and the detailed thermodynamics and chemistry involved with such systems. We basically dealt with homogeneous systems, either H2O or a chemically homogeneous air with a molecular weight of air, specific heat as well. So today we're going to start explicitly looking at thermodynamics associated with mixtures of gases. Whether that mixture is air, H2O and nitrogen plus trace gases, or a mixture of methane, oxygen, nitrogen, or CO2, or H2O vapor and nitrogen, various mixtures of different chemical components or elements or molecules. So we're going to spend the rest of the semester here dealing with chemistry, the chemistry associated with more complicated thermodynamics problems. We're going to start looking at chemistry. How do you deal with reacting systems, systems involving combustion, releasing heat from burning methane and air, releasing heat from burning gasoline, diesel, hydrogen. So we're going to talk about chemical reactions. We're going to talk about mixtures. So we're going to start off here pretty slow, reviewing a bunch of stuff from basic chemistry. So we'll start off today with a relatively short lecture, which includes how we describe mixtures in terms of their chemical composition. So we'll talk about mass and mole fractions. We'll also talk about how the mixture is represented in terms of a homogeneous system. We'll talk about the molecular weight of a mixture. Okay, we'll define a molecular weight for a mixture, and then we'll do an example calculating it. And then we'll do an example here. We'll derive how to calculate molecular weight of the mixture. And then we'll do an example involving gas mixtures. So we'll finish off with an example today. Okay? Okay, so let's get started here. Let's get started. Let's say I have a mixture, and this mixture is composed of various components. So I have the individual atoms or molecules inside this tank. So I have a tank or a chamber filled with various molecules or atoms, components. Each of these different colors could represent an individual nitrogen molecule, H2O molecule, oxygen molecule, or single atoms of material, who knows? The point is the different colors here represent different component molecules, atoms, or particles, okay? So now how do we describe this mixture? This is a mixture of different chemical components. So how do we describe chemical mixtures? The easiest way to describe a chemical mixture on a component by component basis is the mole fraction. So Y sub I represents the mole fraction of the element I or the component I in the mixture. And specifically is defined as the number of moles of element or component I divided by the number of moles in the mixture. We also have the mass fraction, X sub I. That's equal to, so that's the mass fraction of component I. And that's defined as the number of kilograms or the mass of component I divided by the mass in the mixture. Needless to say, the number of moles in my mixture is equal to the sum of the number of moles summed over all components, and the mass in the mixture is equal to the sum of the mass of all components, summed over all components. Okay? Now, we can actually ascribe an aggregate or overall quantity for the mixture, and the most obvious one is the molecular weight of the mixture. The molecular weight of the mixture is defined as the mass of the mixture divided by the number of moles in the mixture. Okay? Well, that's a basic definition for molecular weight of the mixture. How do we calculate the molecular weight of the mixture? Well, so this mixture has some molecular weight. It has some description in terms of mass and mole fractions. That's how we describe the mixture. How do we actually calculate the molecular weight for the mixture? Maybe in terms of these mole or mass fractions. Well, the mass of the mixture is equal to the sum of the mass of each component in the mixture. So sum over all components in the mixture. And the mass of each component in the mixture is equal to the number of moles of each component times the molecular weight of that component, summed over all components in the mixture. So this Mi is equal to the number of moles of component I times the molecular weight of the component. Okay, so I'm just making a substitution here. So now I divide by the number of moles in the mixture. Let me bring in the number of moles of the mixture into the summation. So I get the sum of the number of moles of mixture of component I divided by the number of moles in the mixture times the molecular weight of the component, sum over all components. Now, Ni over N mix is the mole fraction of component I. So the molecular weight of the mixture is now equal to the sum of the mole fraction times the molecular weight of each component summed over all components. So away here to, oh, it's a good place to do it. So this thing has a molecular weight, and the molecular weight of the mixture is equal to the sum of the mole fractions times the molecular weight of each component, summed over all components. So put a little box around here. This is how you immediately calculate the molecular weight of a mixture. You have to calculate the mole fraction. You need the molecular weights, just sum over all components. Now, knowing this, how do we convert back and forth? How do we convert back and forth between mole and mass fractions? How are they related? How are mole and mass fractions related? Well, the mass fraction of a component I is equal to the mass of component I divided by the mass of the mix. So that's the definition of the mass fraction. So there's a certain amount of mass of helium in here. There's a certain amount of mass of mixture. I take the ratio of the two, and I get the mass fraction. I'm sorry about this. I seem to have, sorry about that. A lot of interruptions today. Okay, so let's expand the mass for the component I and the mass of the mixture. Let's see here. The mass of component I is equal to the number of moles of component I times the molecular weight of component I. That gives me the mass of component I. The mass of the mixture is equal to the number of moles in the mixture times the molecular weight of the mixture. Let me group together the number of moles in the component divided by the number of moles in the mixture. And then I got the molecular weight of the component divided by the molecular weight of the mixture. Note that the number of moles for component I divided by the number of moles in the mixture is equal to the mass, the mole fraction, Y sub I. So the mass fraction is equal to Y sub I times the molecular weight of component I divided by the molecular weight of the mixture. Okay? So if you want to convert back and forth between molecular weight, between mole fraction and mass fraction, the mass fraction of component I is equal to the mole fraction of component I times its molecular weight divided by the molecular weight of the mixture. Put a little box around that equation as well. Okay, so these are important quantities that you need to be able to calculate and understand when you're dealing with mixtures, Okay. Okay, let's do an example here. We have a mixture, a container that contains a mixture of neon and argon, gaseous neon and argon. You can see it right here. The number of moles of neon in the container is 0.0185 kilomoles, and the number of moles of argon is 0.0335 kilomoles. You can see here represented in the schematic. Let's say the blue represents the argon, the yellow represents the neon. We have some sort of a gaseous mixture in there, okay? So what are we supposed to find? We're supposed to find the mole fractions for each component in the mixture, find the molecular weight for the mixture, and find the mass fraction for each component in the mixture. That's the plan for today, all right? Okay, well, let's get started here. Notice I left a couple of things here, so let's go through and do the analysis. So let's make a little table here. Component. The mole fraction for each component, the molecular weight of each component, and then I have the mass fraction for each component. I don't think I need all of this. So I'm going to start filling out this table here. It's pretty simple for just two components, but for anything more complicated, you might need this. I'm going to make the, I'll make sure I'm consistent with what I have in my notes here. Let's do the argon first and then the neon. So we have argon and neon, okay? So let's calculate the mole fraction for each component. So the mole fraction for each component is the number of moles of component I divided by the number of moles in the mix. Now the number of moles in the mix is equal to the sum of the moles of each component. So N mix is equal to the sum of the number of moles for each component summed over all components. Let's see here. N mix, that's the number of moles of the argon plus the number of moles in the neon. Let's see, we add these two together, 0.0185 plus 0.0335, and that has units of kilomoles. And I find the number of moles in the mixture. Find the number of moles in the mixture is 0.5052 kilomoles. 0.052 kilomoles. That's the number of moles in the mixture. Okay, let's calculate the number of moles, the mole fraction for the argon. Let's see here, Y argon, number of moles of the argon divided by the number of moles in the mix. Number of moles for the argon, 0.0335 0.0335 kilomoles of argon divided by the number of moles in the mix, 0.52 kilomoles. Kilomoles cancel out, mole fraction is dimensionless. And the mole fraction for the argon is 0.64. 0.64. 64% on a molar basis of the gas mixture is composed of argon. So I'm going to write 0.64, okay? Now what about moles for the neon? Well, I could go through the same procedure here. I could have N neon over N mix. By the way, the sum of the mole fractions, by the way, the sum of the mole fractions has to equal 1. How do you prove this? Well, the sum of the mole fractions is the sum of Ni over N mix. Take out the N mix because it's constant as far as the summation is concerned. And then I have the sum of the number of moles summed over all components. The sum of the number of moles summed over all components is equal to N mix. So I have N mix over N mix, which is equal to 1. So the sum of Y sub I, the mole fraction, summed over all components in the mixture is going to equal 1. So I can immediately write, so the sum of Y sub I, which is the mole fraction of the argon plus the mole fraction of the neon, has to equal 1. So I can simply write the mole fraction of the neon is equal to 1 minus the mole fraction of the argon. And the argon I just calculated, so 1 minus 0.64, or what, 36%, 0.36. Okay, so that's the mole fraction for the neon. Pretty simple, mole fraction for the neon. Now let's go through and calculate the molecular weight of the gas. Let's go through and calculate the molecular weight of the gas. The mixture. Let's go through and calculate the molecular weight of the mixture. Let's do that right over here. So, molecular weight of the mixture. We have an equation right over here. The molecular weight of the mixture is equal to the sum of the mole fraction times the molecular weight of each component, summed over all components. So I will write sum of the mole fraction of each component times the molecular weight of each component. I have the mole fractions of the two components. I don't have their molecular weight. I need to look those up from some kind of source somewhere. The molecular weight for argon is 39.95. 39.95. And that's going to be kilograms per kilomole. And the molecular weight for the neon is a little bit lighter. What is it, 20. 20.18. 20.18 kilograms per kilomole. So those are the molecular weights for each component. Okay, so now I have the molecular weights of each component. I have the mole fractions for each component. Let's just plug into our expression for the molecular weight of the mixture. Let's see, so this is going to be equal to, let's see here, the mole fraction, I guess I'll write it all out. The mole fraction of the argon times the molecular weight of the argon plus the mole fraction of the neon times the molecular weight of the neon. Let's see here. So the molecular weight of the argon, we just calculated it, 0.64, I'm sorry, the mole fraction of the argon, 0.64, 64%, and the molecular weight is 39.95, and that has units of kilograms per kilomole. And then the mole fraction of the neon, 0.36, and the molecular weight was 20.18 kilograms per kilomole. Okay, you crank that through and you get a molecular weight for the mixture. You get a molecular weight for the mixture of about 32.6 kilograms per kilomole. 32.6 kilograms per kilomole. Kilograms per kilomole, 32.6. So let me write that in here. I guess I'll write it in the schematic. So this mixture here has a molecular weight equals 32.6 kilograms per kilomole. There we go. I'll write that over there. 32.6 kilograms per kilomole. Molecular weight, mixture, 32.6 kilograms per kilomole. There we go. Okay. Let's calculate the mass fraction now. Let's calculate the mass fractions. Well, the mass fraction for any component is equal to its mole fraction times the molecular weight of that component divided by the molecular weight of the mixture. We have the mole fractions and the molecular weights for each component and the mixture, so it's just a matter of plug and chug. So let's calculate the mole fraction for the mass fraction for the argon. So that's going to be equal to the mole fraction of the argon times the molecular weight of the argon divided by the molecular weight of the mixture. So let's see here. That's going to be equal to 0.64, 39.95 kilograms per kilomole. That's the molecular weight for the argon. And then we have the molecular weight of the mixture, which is 32.6 kilograms per kilomole. Kilograms per kilomole cancel out. Mass fraction is dimensionless. Mass fraction is dimensionless. And so I get the mass fraction of the argon at 78% or 0.78. 0.78. Again, I could go through and crank out the mass fraction for the neon and do the calculation all over again, but I will say the same holds true for mass fraction as for mole fraction. The sum of the mass fractions is equal to 1 when you sum over all components. And the proof is exactly the same as what we did for the mole fraction. So I'm just immediately going to write the mass fraction for the neon is equal to the 1 minus the mass fraction for the argon. So that's 1 minus 0.78, or if you like, 22% or 0.22. 0.22. So that is the mass fraction for the neon. Notice there's a bit of a difference between the mole fractions and mass fractions for the various components. The reason for that is, for example, the argon is much heavier than the neon. So even though it has only 2/3 of the number of moles, it has nearly 4/5 of the mass. Why? Because the argon is much heavier on a per mole basis than the neon. Okay? Very simple example, not much going on here. Hopefully this jogs your memory about basic chemistry and the like. Okay? All right, ladies and gentlemen, I think we're going to stop there. This has been kind of a long week. So keep things a little bit short. Take care, ladies and gentlemen.